we already have two types of identities besides Pythagorean identities. We have quotient identities, and we have reciprocal identities. And quotient identities are things like tan x equals sine x over cosine x. And reciprocal identities are things like sine x equals 1 over cosecant x. So we are looking for a different type of identity, a third type that will allow us to do more types of problems. So what you see here is a diagram set in the first quadrant of the unit circle. And it's a triangle formed by looking at one of those triangles we might set up. Right? If this is our angle theta, right, and this is the terminal ray here. And we say, well, what are the coordinates of those points? Well, normally we'd call the coordinates of that point. We'd say, oh, the coordinates of that point are x, comma y. Right? We went over x and up y to get there, right? Which would mean that in terms of the triangle, this would be x, and this would be y, if we didn't happen to know what they were. But using the Pythagorean theorem, right, so using that idea that we can say something about the intersection of the sides, right, we know that x squared plus y squared must be equal to 1. Well, in this case, we can add a little bit more to that. That gives us a Pythagorean identity instead of a regular identity. And the reason it's called a Pythagorean identity is it comes from the Pythagorean theorem. Using what we know about the unit circle, when we see an x, we know that's really a cosine. When we see a y, we know that's really sine. Those are the definitions in the unit circle. So I can change this identity and I can get, oh, that's cosine theta squared plus sine theta squared, and that's going to be equal to 1. And the result is that if I square the cosine value and I add it to the square of the sine value, I'm going to get 1, which is a somewhat surprising result, but comes from the fact that we have this right triangle that we can build specifically when we're thinking about the unit circle, which means that the radius is 1. So here's our identity written out where it's a little bit easier to see. Cosine squared x plus sine squared x equals 1. And just because it's written this way doesn't mean that's the only substitution we could make. We could think of this identity as really having 3 forms, one for each, isolated for each of the 3 pieces, right? The first one obviously is cosine squared x plus sine squared x equals 1. We could also think of it as cosine squared x equals 1 minus sine squared x. Or if I prefer, I could isolate sine squared x. Say, well, it's sine squared x equals 1 minus cosine squared x. And remember that the benefit of the identity is that it allows us to make a replacement in the problem that we're doing. Right? So by isolating for one of the pieces, I could then substitute in. If I happen to see a cosine squared x in the problem, then I could do a 1 minus sine squared x. The second thing we should think about is whether or not this particular identity allows us to make other identities. Right? So is this the only of the Pythagorean identities? This only relates together 2 of our trig functions. So let's say that I start again from here, but this time I'm going to take every term and divide it through by cosine. So everything's going to be divided through by cosine squared x. And we want to say, well, do we get anything new? Well, cosine squared over cosine squared is 1. Sine squared over cosine squared, well, sine over cosine is tan. So if I have 2 of those multiplied together, I get tan squared x. And then finally, if I have 1 over cosine squared x, that's secant squared x. And all of a sudden, I have another identity, right? This is another Pythagorean identity that relates together 2 different trig functions. So then if we do that, instead of dividing through by cosine squared, if we divide through by sine squared, then we get this third identity. And the three of these together are the three Pythagorean identities, and each one can be solved for any of the pieces. So there's 9 different substitutions that can be made. And these are the ones that we tend to use quite a bit because they allow us to jump between trig functions rather rapidly. Okay, so finally, right, how might I go about proving an identity using the new Pythagorean identities, right? And so we'll prove the following. Remember that when we want to prove something, we're just going to work on one side. All right? So in this case, on the left-hand side, the first thing I'm going to do is say, well, that's 1 plus, right? And then I have 1 over tan squared a. Well, if it helps, right, that's the same as this, 1 over tan a squared. And again, if it helps on the other side, think about the other side as 1 over sine a squared. And then I see some Pythagorean identities, or not Pythagorean, excuse me, I see some reciprocal identities. 1 over tan a should be cotangent a. And then 1 over sine a should be cosecant a. And so I get 1 plus cotangent squared a equals cosecant squared a. Well, if you remember the last slide, then you remember that 1 plus cotangent squared a is in fact cosecant squared a. And remember, the proof is not done until the two sides are identical. But with two sides identical, right, and in this step, us using the Pythagorean identity, that's how we got to the correct answer.